Oh, welcome. Good morning, good afternoon, good evening, boys and girls. How are we all doing today? Yeah, yeah. Um, so you remember? Okay, backing up just a little bit. We were today originally supposed to talk a little bit about I was gonna give a short lecture on port, on why it works on at a distance, etc., etc. Um, but of course, something I've never experienced actually, which was my Apple Pencil decided to not interface with my iPad anymore, and that means I would either have to draw really badly, or go back to Affinity Designer, which I currently do not have any intention of doing. Yes, exactly. We had a last minute sponsorship deal, and what is this? While True Learn won out, so we're gonna talk a little bit more about machine learning. How it goes, what kind of stuff it goes on, etc., etc. Um, Before we start today, I just wanted to talk about a solution to yesterday's puzzle, which everyone laughed at me hilariously for because I couldn't solve it in time. Um, and the solution that I like, literally, I hit the stop streaming button and then I came up with the solution. Unfortunately, though, the solution itself is not actually that interesting. Um, you remember that yesterday our proposed solution was high accuracy at 44.6 seconds, right? And to achieve gold, we want 44 seconds. So we were zero point 0.6 of a second off, and it turns. Oh, ow! I cut myself. When did this happen? Ah, it's all good. Ignore that. And so the solution, interestingly enough, at least to me personally, the solution that I came up with, which was to add another perceptron right here, does actually do this in gold standard time. It just doesn't do it in an interesting way, right? Like, because this it turns out is at least from my perspective now, this is a load balancing question, and it's about getting the right inputs to the right outputs at the right time. Look at this, right? Like we have 93% accuracy, 100% accuracy, 100% accuracy. Well, ignore the last one. The last one is 100% by definition. Um, but hi, Brett. How are you doing today? And so the solution I ended up using was to add essentially what amounts to be a load balancing. Well, okay, I call it load balancing, but it's more output balancing, right? Essentially, what I'm saying is, if you remember, we were off because output stream 4 was not getting enough output. Was not getting enough output by 0.6 of a second. So essentially what we did is we took the two outputs that come out of here, and then we did a three-way split on them. One third goes into output stream 4, and it's not exactly one third, right? Because you'll notice that I'm only taking the circles out of this. So essentially what I am doing is I am taking the 20% failure rate that are circles here, and I'm putting 80% of that in here, and I'm taking everything else, and I'm taking the 20% failure rate of those two, and I'm putting it in here. I'm well, Brett. Thanks for asking. Glad to see you again. What was I saying? Yeah, and so essentially, the point is that this is a gigantic faff, and this should never have been needed, which means the level designer probably had a different solution. Probably had a different solution in mind than the one that I came up with. Especially given you guys will remember, right? Like that our output is dramatically better than what they expected. So we're doing it at a much higher accuracy at a much faster time. or much faster, quote unquote much faster. Anyway, so that particular the question answered. No, well, so that's the thing, right? Like it's not, how do we say, it's not that their answer would have been bad. It's that their answer wasn't intuitive to me, and that comes back to the whole machine learning issue that we've been talking about since the very beginning, which is that machine learning is such a complex and multi excuse me, just water, no. Yeah, I don't know what I'm trying to say. Essentially what I'm trying to say is there is no one right answer, because we're not trying to, like, it's not deterministic. No matter what you see here, like, this game is very deterministic in where things go and what things happen, but it's in real life, machine learning is non-deterministic, because your input data set is never going to be clean, like really clean, right? Like, the whole point is, if you can already clean it, then you don't need machine learning to actually sort it or do anything on it for you, right? Like, the whole point of machine learning is to clean your data set for you, and so, like, there will always be errors in it. So it's a balance of different factors, and to get to the correct accuracy and the correct speed that you want, right? Like, we have to accept some inaccuracies, and for people who don't understand that, who think machine learning gives you one right answer, they are wrong, just like they are about so many other things in life. Anyway, text recognition. Let's continue. Based on the Rosenblatt perceptron, we need similar vowels from consonants. More accuracy. First, what? Rosenblatt. Cute. Okay, so you need higher accuracy. We have only one. Oh, that's wonderful. And I'm only allowed to use one of them. Oh, okay. So we'll handle this, and we'll go in this direction. Let's do some training. And coincidentally, the way I solved that particular question from before was simply to look at the the inputs. As bad as that sounds, yeah, unfortunately, that's all I could do, right? Like, it's terrible. Yeah, I know. Like, I can look at the input stream, and I just tailor my output towards that input stream, and there we go, right? Like, this is all there is to it. That's not right, is the point. Yeah. What are we doing? One quick second. We're trying to launch our self-driving taxi service, but we have a problem. Makes a lot when it tries to recognize traffic lights. The code, invest 4,000 into this. Yeah, why not? You don't need to train your while working, and they already have the minimum because time is marked. Wow, thank you so much. Wow, thank you so much. Oh, we don't want to do this actually. It needs to be 90%, and this isn't 90%. So that's what we have to do here. We have to make sure that all of our triangles, let's add a little YOLO, right? There we go. Right, so this means that 20% of 20% of the errors goes through, right? And that's essentially 4% of the error, right? Are we clear on how it got 20% of 20%? So 20% of things that come out of the triangle thing are not going to be triangles, right? And 20% of triangle things that come out of the triangle thing aren't going to be triangles here. But we already know that everything coming into here is 20%, is going to be 80% triangles and 20% other things. So everything that comes out of the triangle here is going to be 20% of that. So you divide 20% by 5, that's 4%. Done. It's not quite that simple, but it works in the grand scheme of things. You saw that triangle move away, right, just now? That poor triangle. Oof, look at that. Oh, no, we can't have that. Yeah, we can't have this. We can't have this. This needs to actually feed back into here. No, actually, we're just not gonna have this. Because for the same reason, right? Like 20% of everything that goes in there is, yeah. My bad. There you go. 85%. Yeah. We could add more, right? They give us 50 in total. So we could theoretically add more. If we did add more, it would be like this. It would be like this. To make sure that things continue to go in the right directions. We can take a look and see how that goes. That should increase our accuracy. I think that'll decrease our time though. Look at the triangles just like fucking off into the... Oh, that's just bad. Why are you all going over there? It's supposed to be a 20% chance. Look at that. Look at the amount of triangles that are moving off. That's so bad. Like, we're losing so much accuracy. Okay, let's do this. We could actually do something more interesting like this, right? Which would essentially loop these things over and over until. But at some point you're losing out. Like at some point you're just losing. So triangles that go that way. That's stupid. Actually, you could theoretically, if you think about it, you could theoretically loop it like this. Right? Like you could theoretically do that. And then that everything that comes out of here will go over there. Yeah. Actually, why don't we do this since we have the processing time for it anyway? Wait, what? Oh, no. This would go in here. This triangle will go over here. And then this would go in here. I think that's how it works, yes. Let's see how our accuracy improves. There you go. Right, essentially the more accuracy you put into the system, the better it is. We wouldn't do this, we'll probably do that. Let's try that again. Like the more layers you put in, the more likely you'll be able to select for exactly what you want is true for basically all things, right? So yeah. And this is pleasingly symmetrical, right? I hope you guys can see that. Yeah, this is very pleasingly symmetrical. It is a little bit slower, but it's not that much slower if you notice, actually. Oh, look at that. It's not hitting 90%. How annoying is that? Also, that one's pretty cool. Oh. Okay, so we'll bounce this one to here and this one to here. Does that make any sense? No. No, that doesn't make any sense. No. This one should go here. And then these two should go there. And then this one should go here. These two go over there. Well, I know at this point I'm just fapping around with this. Well, it's true. At this point, I'm not doing anything productive for this particular one. A particular one, we already know how it's going to look like, right? Like this is just it. We could have just simply done 2 more and then be done with it. Like we could have done these 3 and be done with it. But I think, oh, this one isn't linked properly. Okay, release. Oh, right, we're supposed to go next. All your customers usually are shown in red color. Solve this problem for this startup. Okay. Yeah, so that's load balancing. Let's see. Okay. The word. We're using a lot of cat cloud for that. That's okay. What does that mean? Summary, okay. Balance. Okay. Our users are going down. Oh no. I see. Alright. That's not good, is it? No, nobody's using our thing anymore. Okay. Cash out. Just abandon shit. That's exactly it. Wow. Yeah, that sounds about right. Having VR goggles makes you more enticing. Reinforcement learning. Oh, nice. People who love cats with no humans inside, no hands. At self-drive. Dr. Meow W Cats human person. Brand surgery. Oh, look at the least amount of rewards we have. Task nodes work in a different way. All data is to recognize it and then transmit it to the reinforcement learning. Oh, lovely. Oh yeah. Scale invariant feature transform. Yep. Yeah, so you're supposed to recognize these things, and you're supposed to then tune it in such a way that the RL agent is able to understand what these things are. Does that kind of make sense? So it's just one in, one out, but this thing, you have to tune this. Training and testing, yeah, it acts basing on data you've been recognizing when you're building a scheme. Our process from the scheme, blah blah blah. Your car won't be capable of learning it. Okay, the goal in this type of task is to make the AI clever enough to be target average speed limit, supervised learning, drive the track. Oh, okay. Okay. Oh, I see. So we have to tell the car what is an obstacle and what is not an obstacle. This is all road. Oh, I can't do that. What? Press mean speed deviation AI call. What does auto evolve mean? No idea what it just did. So okay, so in the real world, what would happen is we would have one of those shape well, we would have a whole network of this stuff, and then we would actually drive the car with inputs from all sorts of things like lidar, like speed, humidity, all sensors come together in one sort of unit like this, machine learning unit like this, and the car is supposed to learn based on all of these sensors what to do when one of the sensors gives us an interesting information, right? So for example, if the lidar sensor at the front notices that there's someone there, what happens, right? So the point then becomes, it's not even fully about your machine learning unit anymore. It's about uh it's about how comprehensive your sensor set is, right? So look at that. Wow. Well, that's okay, that's pretty good. But you see what actually happened, right? Our Oh, hi Nex, how are you doing today? Um, what was I trying to say? Like, you saw it break really, really hard, and that's just simply because I didn't know what we were doing when we were training the algorithm. I'm well. How are you? It has been a long time. I hope you're doing just fine. Let's see. Let's do this thing. Parallel calculations. Scientific center. Can you parallelize? Okay, so now we're getting into load balancing. Your nodes need a computing power. Certain nodes require more than one server. The more servers, the more expensive your scheme becomes. Too busy. Don't worry about it. It's all good, my friend. Distributes network, blah, blah, blah. Load balancing improves responsiveness, availability to the least overloaded socket. Requires additional server power. I mean, it happens. It's all good. So yeah, so this is just an introduction to this thing, right? So essentially, what this is trying to do is also note that it's requiring 2 server power just to load balance, and that is very much apt, because we actually do very much need a lot of computing power to determine where goes what, where what should go when, right? Because there's actually a very complex series amount of calculations that go inside here. You can't just monitor the output like it would do in a game like this, right? So, see that? Excellent. Yeah. Except, okay. Sales predictions. What is green again? Oops. This game next is called While True Learn. It's a game that essentially uses puzzles to teach you about machine learning, and it teaches some of our viewers about machine learning. One second. Yeah, and so it teaches about machine learning, and the idea is for some of our private class viewers to actually understand what they're talking about when they go in and talk to clients and stuff. No, it's well, it's not car at all. It's This is the kind of algorithm that goes on a lot in the modern world, for image recognition, for data processing, and all of that. And so it's just the car was only um, a shall we say a simple way of really teaching how how showing us how we would teach a neural network, a machine learning algorithm to respond to different inputs. There we go. Decision tree color. What? I'm confused. Sales predictions. Blah 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 blah. I didn't even read it. Yeah, we just bought a. Okay. Well, I mean this. I'm confused why this is a thing. I don't. I don't get it. Detroit Become Human. I would. I would. I would tear that game to pieces so hard. if I actually played Detroit Become Human, I would be really really mean. Um, I would be really mean to it. Yeah. Well, okay. To our listeners or viewers who don't know what it is, Detroit Become Human is a game. I don't think you guys would have played. Actually, maybe. So Heavy Rain, Indigo Prophecy. Actually, not Indigo Prophecy. I don't think. What was the other one? The Two Souls thing. The one that was that starred not Ellen Page, after he made his switch. Can't remember. Elliot Page. There we go. And what was that game? Something Two Souls? No, it doesn't matter. Anyway, it's essentially an old school adventure game. Yeah, and it's as Next says, you choose the destiny of three. You choose how those characters interact in a game. But the fundamental point or the conceit of that game is that androids exist in this society. It would be deserved, Nona. You were absolutely correct. Oh my god, David Cage. You play as in this society. Androids look exactly the same as humans, but are discriminated against, and so it includes essentially like sort of it's so pretentious. It essentially uses androids that look exactly like humans as shorthand for both racism, the labor movement, and what was the third thing I was trying to say? And class divide, and and together, like it's not a very it's not a very at the end of the day, it is only compelling, or rather, it's not compelling to me. Well, I don't need to be experienced in the game to actually know how pretentious it is next. Because I mean, I have lived. I mean, I'm not that right. I'm in my mid-20s, so but I have seen all of these things happen in history over and over again to know enough to know that our boy David Cage is not going to do it justice in a game like that. And partially it is the idea that if you're going to talk about heavy-handed subjects like that, using androids that look exactly like humans is a little bit how do I explain this? It's a little bit it takes me out of the story, because the fundamental there's a fundamental flaw in that. and that's humans don't work like that. Like, if something looks like a human, acts like a human, and does everything a human does, the human brain doesn't understand that it's not a human. So you will have things like empathy. You will have, especially if they are white, right? And in a Detroit Become Human, like, it's just, yeah. I mean, we could very well try to play it if one of our viewers wants to give me the game in some. Uh, and next, you're right. That's very apt, right? Android steals the work of humans and they kill them, and that's exactly what people did to what was his name? In Detroit in the 1970s, one of the biggest murders that happened was to a fellow called David Chin. He was Chinese, um, but the local workers thought he was Japanese, and in the 1970s, uh, Detroit Detroit was just like getting destroyed by the Japanese car companies, and so they cornered this poor Chinese dude whom they thought was Japanese and just killed him outright. And that is, and that, I would say, is would be apt if the androids didn't look exactly like every other human, right? The only reason, you're right, no, like, anything with symbolism is not going to, like, it's just totally not subtle, right? The problem is that there was no visual distinction. So he's trying to say that every human wasn't racist, that every human was a humanist and against androids. But if the androids look exactly like humans, you're not going to get the subtlety of the racism, of the classism, of all of that. Like you can't just divide society into two camps. That is just wrong, right? Like, what are you, a Republican? No. With mild apologies to some of our private class students. Anyway, that's enough of that. If someone is going to gift me that game, great, we can play it. If not, we're not going to play it. But I mean, I don't mind. I don't mind. We can. It would actually be a very interesting way for us to discuss sort of societal issues while making fun of David Cage. Anyway, back to machine learning. Okay, finding ancient artifact Tesseract. There we go. It is very unstable element which radiates energy in different specters. Good job. Spectrums, presumably. We have almost found out how to use its power to benefit humankind. Let's separate direct flows of energy correctly. Seriously though, like, why would you use sapient things for manual labor known as right? Like that's just silly. That's silly. Okay, so we need a balancer out front. Excellent. We need a trash can over here, and we probably need one of these. Do we? No, we don't. But it needs to be 100%. What? Oh, that's interesting. So the only thing that's consistent here is red and blue. The only thing that's consistent down here is green. So if we did this, green and then blue would come here. And then blue is over there. There's no green that goes over here, right? Yeah, no. Red, blue. Because this is, they're only allowing us to use three. So let's try this. That's not fast enough. we simply do this then? But that's also not fast enough, right? Actually, it might be. It might be. Because then we wouldn't be using a decision tree for that. So this isn't filling up enough. That's not filling up enough. Okay. Huh. Well, this would be really expensive, right? Oh, no. Do is we'll balance this. Red goes down here. NE goes up there. NE goes down here. And let's see, we have 30 greens, so we'll set green over here. Would that work? I feel like that wouldn't work. Yeah, see? That is quick though. But we're not aiming for it. We're aiming for it. Well, I am stuck, but it's more of a question of like now we have to optimize these things, right? The problem is, of course, that it demands 100% accuracy. So we would need, and right now you'll notice what happens is that we don't actually get enough. Like we have the 100% accuracy, we're not getting enough into these two pockets. What did I do before? Oh, it was a balancer, and that wasn't going to work. Oh, I do have to go, don't I? Oh, we're not gonna be able to solve this today. Okay, let's go for another 2 minutes, and then I'll end it here. But well, the optimization question is, we have 25 red, 20 blue, and this is So what if we did it the different way? Green goes up top, and blue goes on the bottom, and it doesn't actually matter. We'll send green up there. We'll send red down here, which means green mostly goes up there. Green all goes up there, red all goes down here, and blue gets split evenly between them. Blue goes here, right? Blue goes here, and then NE goes down there. Let's test that. No, that's not gonna be enough. Interesting. So we hit our target for everything except for that one node. Let's try balancer. Oh yeah, what am I saying? Of course. Red goes down here, and then NE goes in. Oh no, and then because green and blue can go into either of those, so we'll send blue in this direction. Red can go into either of those. Done. Excellent. We made it within time as well. Just barely. Yeah. Okay. So why this worked? Why this worked because of a quirk of the upper part, and that's because the upper part can accept red in either slots, which means I don't have to actually choose for red here, right? I just have to choose for green and blue. Well, I just have to choose for blue, strictly speaking. But if I used an any filter here would mean that a lot more blue would go into that, and that means we wouldn't be able to fill up this slot. So that's why actually, let's demonstrate that real quick. We wouldn't be able to fill. You see, all of it goes in there, right? That's the idea. So by choosing for green specifically, we are essentially saying split green and blue 1-to-1, depending on input, and red goes in either or. And on the bottom, like, this is self-explanatory, right? This is the same exact reason, because green is the same, and we know that there's too little blue. That's why we want to send all of the blue in this direction, and that's why the blue, as it comes out, you see all of it goes in there, right? I think fairly self-explanatory. It is expensive because we're using a load balancer. I wonder if we could do essentially not a load balancer, but a... Well, this is still, technically speaking, balancing the load, but without the expense of the server, right? So essentially we do an any, and that should split things up sort of evenly. But you see what happens. We don't have, it doesn't do it fast enough. So we have to use the load balancer for this. I'm sorry, I'm so pretentious. I hope you find it in your heart to forgive me one day. Anyway, okay, we are done for today. Thank you again, everyone, for very much for watching. You know, in conclusion, download Firefox. Please don't use Google Chrome because it's terrible, disgusting little thing. And oh yeah, with my most sincere apologies, I've wasted 42 minutes of your time today. Bye now.